Good morning. My name is Boden Fisher. I'm a water quality associate with the Ohio State University Extension in Northwest Ohio. I'm glad to be with you this morning and have the opportunity to share with you results from my local area for an eFields project that was statewide. This map shows the scope of this particular soil health survey project, which included 88 fields across the state. The effort was led by Dr. Steve Coleman and Dr. Elizabeth Hawkins, among many contributors. As I mentioned, I'll be sharing a subset of this larger data set, which comes from a 3-county area in Northwest Ohio that you can see highlighted here, where I'm located. So the objective of this study overall was to contribute to Ohio's soil health data set. The goals within that were to help us understand the relationship of soil health indicators to soil type, cation exchange capacity, improve general recommendations regarding practices that may impact soil health indicators, help participants set a baseline where their soils are currently so they can monitor changes over time, and help refine soil sampling recommendations based on results from various depths of soil sampling. So the protocol involved was fairly straightforward. We, in each field, followed a zigzag sampling pattern to obtain a representative sample. The main thing unique to this study was that at each sampling location, we took 3 soil cores, one at a 0 to 4 inch depth, one at a 0 to 6 inch depth, and one at a 0 to 8 inch depth. As I mentioned, refining our understanding of how depth affects soil health measurements was a key component of this study. Lastly, the fields I sampled were all sampled between June 26th and July 2nd. Generally, we would go for a little earlier than that, but to avoid fertilization issues, I sampled all soybean fields, so no side dress or anything like that. One of the biggest factors in managing our soil health, as we call it, is our soil's pre-agricultural state. This is associated with our soil types and textures and may set some boundaries or limitations on our overall potential for improvement, or at least the rate of improvement and change. It can help us understand what realistic goals and results we may expect. As Dr. Steve Coleman mentioned throughout the study, the results we're seeing may be best utilized as a baseline for individual growers to measure their progress over time, rather than something to compare across the road necessarily. However, we do want to gain a general understanding of how management and sampling strategy impact soil health parameters across the state. So looking at the highlighted area here, you can see that I'm in the glaciated region of Ohio, and many of our soils are in the higher range for the state of organic matter and also higher clay content, and accordingly, often a higher cation exchange capacity in general. So that's where we're starting from, per se, for the samples that we're about to look at across these 10 fields, okay? So when we talk about soil health, we often mention that there are 3 main components to consider, and all are important for a holistic view: chemical, physical, biological. We often look at chemical when we do our routine soil fertility sampling, so most of us have experience with that. This was included in the study. What was also included in the study was the physical component. The indicator used to describe that was soil aggregate stability, which is a soil's ability to maintain its structure submerged in water. But for my short time here, I'm going to focus on the biological component, since that's a little newer for most of us, as well as the effect of sampling depth on that biological component. So the indicator used for this study to account for biological health was permanganate oxidizable carbon, okay? This is basically the readily available carbon pool that microorganisms have available to utilize. This has been shown to be sensitive to management changes and is also a fairly inexpensive test. So we're looking at the active carbon portion of the active pool of our total organic matter content. So as previously mentioned, soil type has a huge impact on all soil measurements, and comparing indicators among soil types and across soil types in the state takes a lot of analysis. However, we know that cation exchange capacity is a reasonable indicator or predictor of our soil type. So sandier soils generally have a lower cation exchange capacity, while as our clay content increases, our cation exchange capacity also increases. So this study looked at CEC in relation to the other sampling parameters. That way we have a little bit more of an idea of how our soil texture and cation exchange capacity is going to impact these measurements, okay? So that tells us from this, looking at this particular graph, we can see that there's a positive correlation in these samples for active carbon and increasing with cation exchange capacity that is higher, okay? So we see that positive correlation here, and that tells us from the start that soil type and texture may have a significant influence on the results, besides the management practices that we want to learn about. I don't have time to cover each management practice, but we'll go ahead and look at cover crops and its relationship to active carbon in this set of samples, looking at the use of continuous cover crops, meaning cover crops each season. In the 10 fields that were sampled here, there was a positive correlation between more years in cover crops and higher permanganate oxidizable carbon readings, okay? You can also see the limitations here, though. There is scatter on this graph. There's also the maximum was 7 years in cover crops, okay? Many folks have more than that, so that's impactful. And remember, again, we're looking at 10 fields here. So I refer you to the larger study, which also showed a positive correlation of cover crops and active carbon. Now let's go ahead and turn to sampling depth. So we generally think of our top layer of soil being our most fertile and active, especially now on average using less intensive tillage regimes. This study's results are in line with this train of thought. For example, here, looking at sampling depth on the bottom axis and active carbon on the vertical axis, you can see that increased sampling depth decreased active carbon readings. So this was expected, but not a lot of work had been done on this, so it's good to have this understanding for the state. Here's that same data we just looked at, but in discrete categories here. So here we see the averages, okay? This is the average reading for each sampling depth. And you can see again that 0 to 4 inch depth gave us the greatest active carbon reading. One last time, look at this in a different way, showing on a field by field basis for the 10 fields that I sampled. You can see in 8 out of the 10 fields here, the blue bar was the highest or active carbon reading, and that is the 0 to 4 inch sampling depth, okay? So in 8 out of 10 samples in this particular subset of data. So hopefully this has given you a little information on what we did this year. This is sort of a zoomed in view to a small portion of the larger data set. Remember, these were localized results and 1 year of sampling for me, but I again refer you to the larger study for a little bit more robust data, and I think we're learning a lot. And despite the limitations of this subset of data, I hope that this has piqued your interest in the study overall. And to see those full results, you can go to page 222 through 225 of this year's eFields report, okay? And more so than that, I encourage you to tune in this week to our Agronomic Crops team's Soil Health series, where Dr. Coleman and Dr. Hawkins will explain in more detail the statewide results. You can register for that event at this URL at the top. Good to be with you this morning. Boden Fisher, Water Quality Associate with the Ohio State University Extension. Thanks to the Digital Ag team.